So there are two inputs X and Y, each one is the end bit wide. So we connect it to the A and B external signal, A and B, they can be registered or immediate data. By using the multiplex, we can select between them. There is a carry input and as a result we have a G. G is equal to the X plus Y plus carry input. So if carry input is 0, then it is X plus Y. If carry input is 1, then X plus Y plus 1 and. What is the Y? Y can be selected from different places. So there is a block diagram here. B input logic, for example, a multiple Excel can be used here or some other combination of circuit to select one of the possible inputs. So for example, we have two selector, so we can have 4 possible inputs for the Y and they can be selected here. So this is not a correct block diagram of the input logic because there is only one input. There should be, in this example, 4 different inputs. And one of them is B, another ones can be something else, so B complement or you can connect it to AND with 0 and B1 and select one of them here. But maybe they want to implement this part inside the block diagram. So as the actual input we have only B have 1. B, the other inputs which are the B complement, always 0, always 1 can be created by this input. It doesn't necessary to give it to the diagram. So one external input is. So we can implement it by multiple 4 by 1. Or you can create another type of combination or logical circuit here. First, let's explain what type of operations can be done by this circuit. So as you can see, since we have two inputs as 0 as 1, there will be 4 different 0 0 0 1 1 0 1 1. The input Y. This one Y will be inputted from different sources. If the 0 is 1 or 0 0, as the input of the ALU from the 6 input all zeros will be given, and if it is 1 1, all ones will be given to the ALU. So this is my ALU. One of the inmates are coming from the A, another. This is X. This is Y. Another input is coming from a circuit B and B, and there is a circus here which receives to be as 0 as 1. So this and B it can be equal to B complement of the B, all zeros, all ones. So these are the 4 possible inputs to the other. And with other generate G equals X plus Y plus carry input. There is a carry input bit here. What is the output for this? 4 possibilities when S0 S1 or 0 zeros. This is the end with 0 here. We should create a circuit to give their input. Y all zeros. Then what? We have a plus 0. A plus 0 plus carry in. So carrying can be 0 or 1. So a plus 0 is a plus 0 plus 1 is a plus 1. So these are 2 possible outputs, or a plus 1A is the same as the input. So we call this operation transfer. Their input A is transferred to the output of the ALU. So this is not the actual operation, but we need it sometimes. But this is the actual operation. The output of ALU is the 1 unit more than the input A. A is incremented by 1++ in Java and C, so this operation giving A to the other 0 to these 2 bits and then end with 0 should be given to the second input of the other, and the carry input should be also 1. If you select 0, 1 from the combination or circuit that I talk about in the previous part, then we are going to give B to the end bit other. So as a result, A will be plus with B plus C in. So if C in is 0, a plus B plus 0 is a plus B or some simple addition. But if a plus B plus C in and C in is 1, then it is this value. What is this value? We call it add with carry. Add with carry. Is it necessary to perform operations in more than in bits? For example, if my CPU is an 8-bit CPU, then you can only add 2 numbers that are in the size of 8 bits in one instruction and learn another microcontroller assembly in the embedded system, which is an 8-bit processor. And we have an instruction at a special register known as accumulator and a register, for example, or 0. So this instruction in 1851 assembly language means that I'm going to add accumulator with or 0, and the answer will be inside the accumulator as the result. So this is the only size of the data that can be added with the 1851. And as you know, 8-bit data is between 0 to 255. So does it mean that my CPU cannot perform this simple addition? If it cannot perform this simple addition, how can I use it? 8. You cannot add these 2 numbers by one instruction, but you can write a program for this purpose. For example, this is a 16-bit number, so you can consider it as 2 bytes and also the other ones as another 2 bytes. Then the first 2 lower bytes will be up together and compute one part of the result. The other 2 bytes should be add together. But also you need to consider the carry that is generated from the previous low byte addition. So this is the time that we need add with carry instruction. That is necessary for performing operations more than the capability of the processor. If you have any processor, the maximum size of data that you can process is n bit, but if you want more than n bits, you should divide it into some smaller part. Perform them one by one and combine the result. Adding to 16 bits number with an 8-bit processor is in this way. First, at the first low byte, find the summation by using a simple add. For the next 2 bytes you should use add with carry. Carry of the previous additions should be considered. So what is the other one? If carry 0g is equal, a plus b complement, which is the subtract with butter. This is, again, like the add with curry, can be used to extend the size of the data that can be processed by the processor. And this is the actual subtract a plus b complement plus 1. The complement plus 1 is to complement. So this is the minus p. A plus, minus b means a, minus b. So in order to subtract it, 1 0 should be given to them as 0 as 1. Carry input should be 1. Then the other. Give me the subtraction. And what about the old ones? If I add a plus 4 or 0. Pillars 1111. Assume that all 0 size is forbidden. What is the meaning of this operation? R0 plus 1111. This is minus 1. So this is the R0. Minus the experiment. Well, this is the way that we create decrement. Increment, decrement are subtract, transfer, subtract, we borrow are generated. And lastly, we have this one, which is exactly the same as this one. We perform a minus 1 plus 1. This is minus 1 is and it is minus 1. And 1 unit is coming from here. So a minus 1 plus 1 is a. This is the result that we have again, as the output of the AND. With other. So according to the values of 0 S1, the output can be transferred increment at add with carry, subtract. Or subtract decrement and again transfer. So these are the macro operations that can be done by that circuit. But let's see what is there inside that circuit. It is a logical unit here that you should design it. How the input Y should be, B complement all ones and all zeros. So I'm going to design the circuit for this purpose. So the input logic in the figure can be implemented with a 4-to-1 multiple Excel. This is the simplest way. I need a 4-by-1 multiple Excel. This is the output. This is connected to the Y. This is Y. It is here. So B not, so for B not. I can use a nutcase here. Zeros and 1. But pay attention that these are needs. So we have N different. Not here. And beats which all of them are 0 or all of them are 1. Instead of using a multiple Excel, there is another way to design it. To reduce the gate number. It can be implemented through logic design of 1 bit instead of using a multiple. Let's see. I'm going to design a combination of circuit or 1 bit of that circuit only. As you can see, we consider 1 bit, 2 or AND bit data. We need one circuit similar to this one. So bit index 1. S0 and S1 are the inputs of the block diagram. This is the diagram. Y is the output. The S0 and S1. So we contains N bits here. I'm going to talk about only 1 bit for extended. You should use that circuit that I design N times to create the AND bit circuit for this part of the value. So let's see, what is the combination of circuit? First, you should draw the root table of the circuit. We have 3 inputs, so we have 8 different combinations. When it is 0 0 and B is 0, what will be the output according to this table? When it is 0 0, all zeros should be the result. So for 0 0 it doesn't care about the value of the B, it should be always 0. Let's check it. As you can see, when SE0 is 1 or 0 0, we don't care about the value of the B index. We index I can be 0 or 1, but the output is always 0 or here when S0 is 1 or 1 1. We don't care about the value of the input. B it is always 1. So this is always 1, always 0. And this is the part that we set that when the input is 0 1, the 0 1 or 0 1 output should be B. As you can see, output value is the same as input. This part is the same and this is the B complements 0 1, but as the output it is 1 0. This is the complement. This is always 0, always 1. So this is the way that we fill this table. When 0 is 1 or 0 0, the output of the circuit should be 0 is 2 bits. When it is 1 1, the output should be 1. When it is 0 1, the output should be B. As we can see, B is 0, output is 0, B is 1. Output is 1. When the 0 is 1 or 1 0, the output should be B complement. So 0 change to 1 1 change to 0. After you find the output of the combination or circuit, you can use con of math to simplify the circuit. So these are the mean terms that are 1 in this table, and there is a group of 2 1s here, and these 2 bits can be also considered as a group of 2 bits. So Y output is by n with 0 or with pi prime and with S1. So if I'm going to draw it, there is a gate here, 2 n gates, or here B is coming here P index. I am not of B index. I is coming here. On this part, S0 is here and this one is here. So this is the Y index. So for if I have 4 beats, I should use this circuit 4 times. Let me show you in the next figure. So this is a diagram of a 4-bit arithmetic circuit. Well, as you can see, we have 2 inputs A and B, so A is equal, a 3, a 2, a 1 and a index 0. And B can be represented by B3, B to B1 and B0. We can see to each of these levels I give 2 bits, a 0 P0 a 1, B, 1A to B2 and a 3 V3. One of them is completely given to this full other. And as you can see, the carry of the one level is coming to the other level. So this is the way that you can create a simple n-bit other. The first carry input of the first full order is connected to the scene, and this last carry output is considered as the output. And this is the result of the end bit at G0, G1, G0, G1, G2, G3. So this is the LSB. This is the most significant bit, the leftmost bit. And this is the circuit that I talk about it. We designed it in the previous part to select between the S0 and S1 and B0 and B prime. So as you can see, for example, here, B and B prime are given to here we have S0. Here we have this one. This is the object that I draw and it is connected to the Y to all. You can use a multiple. So here, a 4 by 1 multiple Excel. But of course, This circuit is more simpler. It contains a smaller number of gates. So till this point, we designed the arithmetical part of the. All the other operations that can be performed by each clue is logical operations for the logical operation. We have some simple micro operations like AND, OR, it's OR. And not these are the 4 simple macro operations that are going to make it possible for my ALU to perform it. And pay attention that these are the kind of 2 bytes or 2 and big data. Like something that you learn in the assembly, for example, 1101. I'm going to explore it with 110. What will be the answer? 0x or with everything is the same. So you know from the Boolean algebra AX or with 0 is A. Explore with 1 is a prime, so 0. That's not one change. It will complement 1 complement it, 0 does not change. So this is the result. So in order to make it possible for your ALU to perform it, we need a module similar to this one. So here we talk about 2 bits, only a index, IP index. We use a 4x1 multiple Excel to be selector. When it is 0, 0, the input 0 will be in the output. When it is 0, 1, this will be selected, or this one or this one. So there is a selector to input 0, input 1, input 2, or input 3. If SW0 is 1 or 0, 0, then the output is the end of the input, a index, IP index. So in order to make it complete, you should use this circuit n times to implement n of 2 end bits. Data or of 2 n bits data is all for the NOT. Of course we don't need the input P, only we need one input. So as you can see, this is the a high BINAI or by AX or with B index 1, and this is the AI prime. So 4 possible logical operations can be done by this simple circuit. Now I'm going to combine them to create a real 1 level or 1 bit ALU. This is the circuit that I explained it in the previous slide. The 4x1 multiple Excel that select between n of IB or of IBX or not. And this is the circuit that I explained it in the 2 slides ago, and we can perform increment decrement, subtract, add with carry, subtract with borrow and transfer. So 2 bits are here, select as 0, 1 another, 2 bits are here, and the output is given to a 2x1 multiple Excel. So the output of the actual value can be from the arithmetical unit or logical unit. So this is the as to which select between arithmetic or logic operation and as 0, 1 is connected to both of these 2 module arithmetical operations or logical operation, but as 2 will be selected different operations. So if you remember, in one of the slides they mentioned about the S2 as the mode S2 is 0, then it is in the mode of arithmetic. If S2 is 1, then the system is in the logical operation mode. A and B, I is given to both of the module this year and also another year. And this one here. And another one here. So according to the value of S0, S1, and S2 and C in, we can have different results in the output of the ALU, as you can see when S2 is 0. From this point in this point, the result is coming from the arithmetical part. This is the 8 different arithmetic operations: transfer, increment, add, attempt, carry, subtract, borrow, subtract, increment and transfer again. And when x2 is 1, then the logical module will be activated. So we have an OR, XOR and NOT. So, as you can see, the scene is connected to the S0 of the second module. Let's check back the previous. The scene is connected to the 0. And this is the scene of the arithmetic module. Also we have seen, and still we don't have S1 in the logical. So as you can see, we don't have value for S1 in the logical part because it is connected to the scene and 0. If they are 0, 0, the output is, and if they are 0, 1, the output is, or if they are 1, 0, the output is XOR, and if it is 1, 1, the output is. So for all of them is 2 is 1. For all of this part is 2 is 0. What about the shift operation? There are two different ways to design a shifter by using a simple combination of circuit. As you can see, as an input, we have the 3 B to B1 and B0. There are 4 multiple axles. Actually it is 4 by 1, but it doesn't display the next one. So we have 2 bits value for the SX. Let's check the circuit. If SE is 0, 0, what will be the output? If SE is 0, what is the edge? I'm going to find it. So this will be selected and coming here. And for this one. And for this one, and for this one, let's see. What is the connection? This is connect to the B3, B to B1 and B0. So X is the same as the input, H is equal to the B. Let's check the other ones. 0, 1. This one will be I. R. So it is I. R. This is the MSSP. Left must beat. Right must beat. What is here? This one is connected to the B3. So this is B3. What is this one? It is connected to B2. And this one is connected to the B1. So H. Let me write it somewhere else. Yeah, it is become IRB3E to B1. The input was this value B to B1 B0. And now we have this value. What is this value? This is the same as the input shift to the right one. It is coming from the input I or input right. And all of the bits are moving 1 bit to the right. B3 now is here. B2 is now here. And B1 is here. So when it is 0, 1, this circuit perform 1 bit shift to the right. Let's check what is the value of the output when we have 1, 0 as the value of the SE. So input 2 will be activated. Here. The input tool is connected to B2, so the edge is equal B2. This one is connected to B1. This one is connected to P0 and this one is connected to L. So this is the 4-bit output. What happened to the input? The input was B to B to B1, B0. As you can see now, this data is shift one location to the left. If left 1 bit is coming and all of the other bits are moving one location to the left and this one is disappeared. So we have ILB0, B1, B2. So this cell cannot perform both shift left and shift right for me, but only 1 bit. We need to use M times if you want to shift it a bit. How can I perform more than 1 bit shift by a circuit? Assume that we have a 4 bits number. So this is a 2-root table of barrel shifter, which is a combination of circuit shift or rotate the input data by the number of bits position as specified by a binary value. So if you want to shift data 2 times, 3 times, 10 times, it doesn't necessary to spend more time. All of them can be performed in a same time. So it doesn't relate to the number of shift in the mix. We can shift a data between 0 to 31 bits, so the time to execute the instruction is the same for all of them. So let's check the output of the barrel shifter for a bit more. If the input is 0, 0, then we don't want to perform any rotation. So the output is the same as the input. So assume that the input is the 3D to the 1 and the 0. This is the input. And let's check what is the output for each of these combinations. If it is 0, 1, then as you can see, the 2 coming here. It is the 2 RD1 is here, the 0 is here. So each bit move one location to the left and the tree is coming back from here and come back in this part. So this is the rotation, one position to the left. What about the 2 position? If I'm going to rotate 2 positions. So, if it is the 3D2, D1, D0, by one rotation, the 2 coming here, the 1 coming here, these are all coming here, and 3 more from this position to the spot. Another time, the 1 is here, since the 0 is here, D3 is here and D2 is coming. This is to be rotated to the left. If I'm going to repeat this operation another time, again, this 0 is here. The tree's here. The 2 is here and the 1 is here. So this is the result of rotate 3 positions to the left to position 1 position. So how can I create a circuit to perform these operations according to these 2 inputs? As 0 as 1 I can use for multiple cells, each one for by 1. Select Thor is connected to the 0, 1. For the last bit, Y3, for example. This is, for example, 0, 1, 2, 3. This is input 0 that should be connected to the tree of the input. This one should be connected to the data. This one should be connected to the DH1, and this bit should be connected to the D0. What about this one again? A multiple except for by 1. This is 0, 1, 2, 3. This is the output. Y0, 0 and 1 are connected to all of them. These 0 is connected here. The 1D3, is connected to the input 1, the 2, and the 1. So for the other tools, it can be designed in the same way. Let me show you the circuit of the barrel shifter. So we have 4 inputs: the 3, the 2, the UN and the 0. So as you can see, we have 4 multiple axles. Each one has 4 inputs. And 0 is one which is connected to all of them. So S1 is connected here and here and here. And this is the control signal as 0 and 1. But according to the table, for example, the input tree should be connected to the 0. So as you can see, the 0 is connected one time here. Here it is connected to the input 1, and here it is connected to the input 2. And the next one, it is connected to the input tree. The 1. It's connected to input 0s here. Also it is connected to the input 1 here, input 2 here and input 3 here. So this is the way that we can implement the previous truth table of the bottle shifter. So as you can see, according to the value of 0, 1, I can implement 0, 1, 2, or 3-bit rotation by this circuit. Only it takes 1 clock cycle. We have only 4 registers in the MIPS architecture. We have 32 registers. So the circuit will be very complicated. We represent the registers as a block known as register, file, a set of registers. Having common micro operations performed on them is the register file. Let me show you the block diagram here. This is a register file and registers. Each one has a bit length. For example, we can have 8 registers each, 132 bits, then M is 3 and Pn is 32 to power M registers each 1 and bit. How can I select between 8 registers in this example? I need 3 bits, so I need the address with size 3 or in the general M bit to select A and B. These are the input signal for register file to select one of the register as the A and one of the register as the B, but the size of the output is n bits because each register is in this example, for example, 32 bits. So 32 bits data is coming here and giving to next part of the system. For example, ALU. And the data that I'm going to write is another end bit. This is the data that I'm going to write, and this is the destination address. The destination address. So in the diagram that I show you in the beginning here, this is the destination selector and these are the selector of the input A and input B here. This is the selector of the A and B input. And this is the selector of the destination. This is the common data that is coming to all of the registers. And according to the signal load or write. This is their signal, write. Let me show you right here. This is the write signal. Load. Enable. It's known as write. So load enable and this destination selector select which one should be accept and write the data from. Here. This is the data. the data should be right in each one of them. As you can see, by using the register file, the complexity of the circuit is reduced and it can be now extended to any number of registers. For example, 32 registers. If you have 32 registers or 8 registers, there isn't any difference in the shape of the diagram. We have a register file. You can select one of these registers as the data by using this n bits and one of them from for the bid to buy this n bits, and the result can be stored in any of them by using the destination address. And this is the data that will be stored back in the one of the rest. The other part is the same as the previous data, but we talk about it. All of that is summarized in this table. Shifter also. Aditya. So this is the logical part. This is the arithmetical part, and this is the shift to the right hand left, and this is the one that data will be transferred from B to the output. Sometimes we want to perform, for example, this operation or to transfer to the R1. So this is the operation that we should use it in this system to perform this micro operation. We will continue designing the data path and the control unit of the processor in the remaining